we are finding the area between two curves today. So first page is all definition on what we're going to do. If f and g are continuous and function f is greater than or equal to function g over some interval a, b, then the area bounded by function f and g on this interval a, b is given exactly by the area between f and g is equal to the area under f minus the area under g. And this is given by the formula, the integral from a to b of f of x minus gx dx. So we're going to have three cases to find the area between the curve. Case one is if function f is greater than function g on this interval. So the picture, it shows that function f is above, basically, I guess we could keep that simple by saying if f of x is above g of x, then this will be a case one. So this means that all the y values of f of x are greater than all the y values of g of x, or f of x is above g of x. And we will use case one, and the setup for that will be the integral from a to b of f of x minus gx dx. Okay. Case two is now going to be if f of x is less than g of x. So function f is below function g on this interval a, b, which is again reflected in the picture below. Here is function g, and it is above function f. And if we have this case, then the setup for the integral will be the integral from a to b of g of x minus f of x dx. Okay, so that's case two. And then case three, if we're given some interval AC, and on this interval, if f of x is greater than g of x from a to b, which is given right here, from a to b, let's say that this purple function is f of x, and the x-axis is g of x. Okay, so from a to b, we see that function f is above g. But then from b to c, we see that g of x is above f of x on the last part of the interval. So if this happens, then the setup for the integral is going to be, or the setup for the area is going to be the integral from a to b of f of x minus g of x plus the integral from b to c of g of x minus f of x dx. Okay, so this is a case three. And the case three happens if on the same interval, f of x is above g of x, and then g of x is above f of x. So case three. Okay, I could have left all that there except for that. There we go. Okay. So those are our cases. Now let's put them to use. Okay. Example one. Find the area bounded by y equals negative x squared plus 20 and y equals 0 for negative 3 to 3. Sketch a graph on the given interval, and we're going to determine what case it is, and once we figure out what case it is, we'll find the area. Okay. So it is important to actually graph these functions out. But what's great about it is that it's giving us the x values to choose. It says, choose the x values from negative 3 to 3. So just like my instructions say above, we're going to make XY charts for each function. And we can definitely use Desmos, which we will. Let me go ahead and make those XY charts. Okay. So we're going to say that this is for y equals negative x squared plus 20. Here's my XY chart. And we're going to pick the numbers. It told us negative 3 to 3. So negative 3, negative 2, negative 1, 0, 1, 2, 3. And then why not build an XY chart for the next function? Y equals 0. Here's XY. And again, -3, -2, -1, 0, 1, 2, and 3. Okay, here we go, Desmos. Hide video, hide that. Move you over there, move you here, and then get me a new one. There we go. Okay. So here I will start with -x² plus 20. And then I'm going to do my table, and we're going to go from -3 to 3. Oops, that's 23. Okay. So -3, 11, 16, 19, 20, 19, 16, 11. Perfect. And then for the red one, we don't need to use Desmos because no matter what X value you pick, Y is always going to be 0. So 0, 0, 0, 0, 0, 0, 0. Okay, which means let's go ahead and graph this. So let's look at our graph. Let's make our intervals appropriate. We're going from -3 to 3. So for this guy, here is -3, -2, -1, 0, 1, 2, 3. And then for my Y values, the highest I go to is 20. So let's go ahead and do this by 2s. 2, 4, 6, 8, 10, 12, 14, 16, 18, and 20. Okay. And now I'm going to plot my first function, which is the XY chart that's on the left side still by Desmos. And we had -3 and 11, which is going to be in between 10 and 12, of course. -2 and 16. -1 and 19. So right around there. And then 0 and 20. 1 and 19. 2 and 16. And then 3 and 11. Doesn't have to be perfect. So here is our graph of -x² plus 20 from -3 to 3. So all of this is f of x. Okay, next we're going to draw g of x, which we're going to call y equals 0. And that was just for every x value, y was 0. So this is the line we have. We start here, we end there, and there's g of x. And now our goal is to find the area between these two functions. So we're trying to find all of that area between these two functions. So now let's go ahead and see what case we have. Okay, so that was step A. We sketched everything. So I'll say A. And then B is just determine what case we have. So if we look at our graph, we see that f of x is above g of x. So from our graph, f of x is above or greater than g of x. So this is going to be a case 1. A case 1. Okay. Which means for the case 1 setup, the integral is going to look like this. It's going to be the integral from a to b of f of x minus g of x dx. There we go. So there's our setup. And now we can go on to step C, and using the case above, let's go ahead and set up our integral. Okay. So C, we're going to get the integral, and the x values they gave us were from -3 to 3. So it's going to be the integral of -3 to 3 of f of x, which was -x squared plus 20, minus g of x, which happens to be 0 with respect to x. Okay, clean this up, and you get -3 to 3 of -x squared plus 20 with respect to x. And let's just go ahead and use Desmos now. So we can just go ahead and plug this in the calculator. So let me come down here, and I'm going to say the integral from -3 to 3 of -x squared plus 20 with respect to x. And we find out that the area between these two functions is 102. And there you go. That's everything you need to do. So any questions on that? All right. And if you wanted to go a little more in depth, this is actually pretty cool. So if I got rid of the squiggles here, what you're actually finding is the area of a finite amount of rectangles underneath or in between both functions. So watch this. So here would be considered, let's say, here's one rectangle. Here's another rectangle. Here's another. Oh, we could probably go all the way up. There's another rectangle, and there's another rectangle. So all of these rectangles, if you were to find the area of each rectangle and add them, you would get a number very, very close to 102, which is pretty cool. But we don't have to worry about that too much in here. So again, all we're doing is finding the area between those two curves. Okay. Sweet. So that was case one. Let's go on to the next. Okay. 2. Find the area bounded by y equals -4x minus 6 and y equals 0 for -1 to 2. So there's our interval, -1 to 2. And again, we're going to sketch everything. Okay. So here's going to be A, and we have the first function y equals -4x minus 6. Make my XY chart. And once again, it's telling us what x values to use. It says use the x values from -1 to 2. So it's telling us what to plug in. -1, 0, 1, 2. And Desmos for the win. -4x minus 6. Use the chart. And -1. Actually, I think all those numbers are there already, right? Right there. -1, 0, 1, 2. Perfect. So -2, -6, -10, -14. And then once again, our next function is just y equals 0. So we get that same XY chart that we did on the last problem. So for -1, -2, not -2, sorry. -1, 0, 1, 2, the y values will always be 0. Okay, perfect. Let's go ahead and graph this and make our intervals appropriate. So here's -1, 0, 1, 2. And my y values go down to -14. So that means that for my y-axis, this will be -2, -4, 6, 8, 10, 12, 14, and negative, 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 negative. Okay, I'm going to plot the first function, and we're at -1, -2, 0, -6, 1, -10, and 2, -14. So here's our f of x. So here's f of x. Okay. And then g of x is going to be just like the last problem. It's going to be a horizontal line on the x-axis from -1 to 2. And there's g of x. Okay. And once again, we want to find the area between these two functions. Okay. Not like it. There we go. There we go. There we go. Okay, better. Okay. So now we want to know what case we have. And by looking at the graph this time, g of x is now above f of x. So g of x is now above f of x. So for part B, we have that g of x is greater than f of x. So this is now a case 2. And the setup for that integral is the integral from a to b of g of x minus f of x dx. Okay, so we're all set. Let's go ahead and set up our integral. C. We have the integral from -1 to 2 of g of x, which is 0, minus f of x. Make sure to put it in parentheses, which is -4x minus 6 with respect to x. The reason we put this in parentheses is so this negative can distribute. So let's go ahead and clean that up, and we will get the integral from -1 to 2 of, and that is just 0 plus 4x plus 6 dx. And we can type that in. We don't need the 0 there, but I just have it there just for the next step. So when I type this integral in, I'm just going to say the integral from -1 to 2 of 4x plus 6 with respect to x. And we get that the area is 24. Boom. There we go. Okay. Guys, good on that?
Yep.
All right. Perfect. Let's keep moving. 3. Find the area bounded by f of x equals -3x and g of x equals 0 on the interval -3 to 2. Okay, so here we go again. F of x is -3x. So step A, f of x equals negative 3x. And here's my XY chart. And we had said from negative 3 to 2. Okay. Negative 3, negative 2, negative 1, 0, 1, 2. Okay. We don't really need Desmos for this because all you're doing is multiplying all these values by negative 3. So negative 3 times negative 9. I mean, negative 3 times negative 3 is positive 9, 6, 3, 0, negative 3, negative 6. Okay. And then the next function is lucky us again, is g of x equals 0. So the XY chart for that would look like the other XY charts. From negative 3, negative 2, negative 1, 0, 1, 2, the Y value will stay 0. Okay. So let's go ahead and plot this. So negative 3, 9. Okay. All right, there we go. From negative 3 to 2, so let me make my intervals appropriate. Negative 3, negative 2, negative 1, 0, 1, 2. The highest we go is 9. So we can just leave these intervals alone. This will be 9. And the lowest we go is negative 6. So 1, 2, 4, 5, 6, 7, 8. And then the lowest we go is, again, negative 6. Negative 1. I guess we could have went by 3s, whatever. Negative 2, negative 3, negative 4, 5, and 6. Okay. So graphing the first function at negative 3, we are at 9. So we're right here. Negative 2, we're at 6. Negative 1, we're at 3. 0, 0. 1, we're at negative 3. And 2, we're at negative 6. Okay. So here is f of x. Try to get it straight. There we go. So here's f of x. And then once again, here's g of x from negative 3 to 2. Let's get our horizontal line. Okay, and now we are trying to find the area between these two functions. So we want to find all of this area and all of that area. Okay. Well, oh yeah, let me put that. This is g of x. There we go. Okay. Now to determine the appropriate case, well, we see that from negative 3 to 0. Here, I'll write that on the graph first. We see that from negative 3 to 0, f of x is above g of x. So let me point that out. And then we see that from 0 to 2, g of x is above f of x. Which means that by step B, if we have on an interval that f of x is above g of x, and then g of x is above f of x, we're going to have a case 3. So this is going to be a case 3. And our descriptions are written on the graph. So the setup for case 3 is going to be the integral from that A. Yeah, from A to C. Is it A to C? No, A to B. From A to B of f of x minus g of x dx plus the integral from B to C of g of x minus f of x dx. Okay, so we are all ready to get set up. So here we go. C. We're going to say the integral from -3 to 0 of f of x, which is -3x minus g of x, which is 0 dx, plus the integral from now 0 to 2 of g of x minus f of x with respect to x. So let's go ahead and clean this up. Let's make this look pretty. From -3 to 0, and -3x minus 0 is just -3x dx, plus the integral from 0 to 2, and 0 minus -3x gives me positive 3x dx. And now we're ready to put it in the calculator. So you're going to get the integral from -3 to 0 of -3x dx. And then plus the integral from 0 to 2 of 3x dx. And we get 19.5. All right, there we go. So we have explored all 3 cases and set up every one of them. Any questions on that process? All right. Got it down, huh? All right.
I got the process down. Yes.
Okay. 4, using production and geological data, the management of an oil company estimates that oil will be pumped from a producing field at a rate given by R of T equals 100 over T plus 10 from 0 to 15, where R of T is the rate of production in thousands of barrels per year, T years after pumping begins. Find the area between the graph of R and the T axis, which we can just call this the X axis, over the interval 5 to 10 and interpret the results. Okay, so this word problem, we're going to handle it the same way we did the other 3 examples. So we're going to first start out with our XY chart and graph R of T, and the interval they're giving us, yes, they gave us one main interval of 0 to 15, but then in the problem, we're actually using the interval 5 to 10. So we're only going to use the numbers from 5 to 10. Okay. So let's go ahead and make our XY chart. So A for R of T equal to 100 over T plus 10 plus 10. And the XY chart goes from 5 to 10. Well, this is going to be a TY chart since our variable is T. And we start at 5, 6, 7, 8, 9, and 10. Okay. So if you're going to type this function into your calculator or Desmos, make sure to just use the variable of x. Okay. So typing this in Desmos, I'll do 100 over x plus 10. And then move over and do plus 10. And now use my table feature and let's go ahead and type in those numbers. 5, 6, 7, 8, 9, and 10. All right. So at 5, we get 16.67, 6, 16.25, 15.88. 8 is 15.56. 9 is 15.26. And 10 is just 15. Perfect. Okay. And there is our first function. The next function, well, in the problem, it says that find the area between the graph of R and the t-axis. So we are basically saying the t-axis, which is the same as the x-axis, which happens to be the same equation that we've been using for g of x on the last 3 problems. So our next equation is just y equals 0. And we know how that works out. So if I made my ty chart and went from 5 to 10, the values would always be 0. So I'm going to do here to save some time is just say 5 and 10, and you get 0, 0. Okay, so let's go ahead and graph this. And we're only using 5 and 10. So here's going to be 1, 2, 3, 4, 5, 5, 6, 7, 8, 9, and 10. Whoops. Okay, and then for my y values, the highest I go is 16 and the lowest I go is 15. So this means that I can just go by 2s. Why not? 2, 4, 6, 8, 10, 12, 14, 16. Sure, we'll stop there. Okay, so I'm going to graph the first function, r of t. And at 5, we're at 16.67. So I'll just put that somewhere around here. And then at 6, we're at 16.25. So just a little bit higher. And then at 7, we're at 15.88. So that's going to drop right below 16. And then at 8, we are at 15.56. So not much lower than that one. And then at 9, we are at 15.26. So getting closer to 15. So here's going to be where 15 is at. So let me just adjust these points a bit. So we're getting really close to 15. And then at 10, we're exactly at 15. So let me see something real fast. Yeah, our function, mine's not the greatest sketch, but again, this is just a sketch. It's going to look something like this.
So quick question.
What's up?
Just for sketching purposes, would it be easier or easiest to get the best sketch, I guess, to kind of have the first integral and then the last integral and just connect the two? just to get a pretty line there. Unless, I guess.
Wait, so say that again.
I just realized what I just said is very stupid, so never mind.
All right. Okay, so here is r of t, and here's y equals 0. But we can even call it g of t if we wanted. And again, we are finding the area between these two functions. So now we see that r of t is above g of t, and that means we're going to be a case 1. Okay. So B, we have a case 1, and we know that setup is the integral from a to b of, and in this case, it's going to be r of t minus g of t with respect to t. Okay, so that means we can move on to C and set up our integral. So we're going to say the integral from 5 to 10 of r of t, which is 100 over t plus 10 plus 10 minus g of t, which happens to be 0 dt. Okay. So now we definitely have some cleaning up to do. Oh yeah, and we have a new antiderivative formula that's above. So we're going to use that today. So this says the integral of 1 over x plus a dx is equal to the natural log of the absolute value of x plus a plus c. So this formula is going to come in handy once we clean up this interval. Or maybe we don't even have to use it at all since we're using a calculator, right? Okay. So all we're going to do here is just clean this up then. All right. So this is just going to be the integral from 5 to 10 of 100 over t plus 10 plus 10 with respect to t. All right. So again, since we're using the calculator, we don't have to worry about that formula above. So we're going to type this function. But remember, if you're typing it in Desmos, replace your t's with x's. Maybe I'll even write that on here, right? I'll just say Desmos. It's going to be the integral from 5 to 10 of 100 over x plus 10 plus 10. There we go. Okay, and now integral 5 to 10 of 100 over x plus 10 plus 10 with respect to x. There we go. And we get 78.77. Okay. So I don't think this problem's done yet because it says find the area between the graph of R over the interval 5 to 10 and interpret the results. Okay. So what we're finding here is the amount of barrels per year, but remember that barrels is going to be in the thousands. So what we're going to say with their answer is that from 5 to 10 years, we are going to produce 78.77, whatever that is, times 1,000. So in the span of 5 to 10 years, we are going to make 78,770 oil barrels. There we go. Because I know this problem, you have one exactly like it on your homework. So just want you to interpret that answer. So I think it'll even have a trick one that says that you'll make 78 barrels, but you're actually going to make 78,000. Okay. Everybody good with that one? Not much different from the other three, right?
Yeah, I'm good.
Okay. All right. So those are areas between two functions. And now the last part of these notes is something called the Gini Index, which deals with something called the Lorenz Curve, which both of these are all about having equal distribution of income among families in a certain population, which we know that that'll never happen, right? That means that everybody's making the same amount of money. Crazy to think like that. All right. So definition of the Lorenz curve. One method used by economists to study the distribution of income in a society is based on the Lorenz curve. The Lorenz curve is found by using regression analysis, a technique for fitting a function to a data set over a given interval. X represents families at or above given income level, and Y represents the cumulative percentage of total family income received. All right. So if you look at these graphs, the line Y equals X is the curve of absolute equality. So the closer the curve gets to this line means that income is being distributed equally among families. But then if you get close to filling, if the curve gets close to filling out the whole triangle, then this means that income is not being evenly distributed. This means that one family or maybe even one person is making all of the income. Okay, so this is how our Lorenz curve works. Okay, so absolute equality of income would occur if the area between the Lorenz curve and the Y equals X were 0. So this means that the curve and the line are touching each other. This means that everybody is making equal income. And then absolute inequality happens if the area between the Lorenz curve and Y equals X reaches 1/2, meaning you have filled out the whole triangle. And this means that all the income would be in the hands of one family. All right. So to represent the ratios between the areas A and B, we use something called the Gini Index. And it's given by the formula 2 times the integral from 0 to 1 of x minus f of x dx. The Gini Index is always a number between 0 and 1. A Gini Index of 0 indicates absolute equality, and a Gini Index of 1 indicates absolute inequality. The Gini Index is used to compare income distributions at various points in time between different groups of people, before and after taxes, and between different countries. So pretty cool. Which means let's get into the last example using the Gini Index, of course. All right. All right. 5. The Lorenz curve for the distribution of income in a certain country in 2013 is given by f of x equals x to the 2.6. Economists predict that the Lorenz curve for the country in the year 2025 will be given by g of x equals x to the 1.8. Find the Gini index of income concentration for each curve and interpret the results. All right. So let's see how income was in 2013, and then let's see how income might be in 2025. All right, so let's go ahead and set this up. Oh yeah, Desmos. Woohoo. Okay. So for A, we're going to do the Gini Index for 2013. So we're going to say the Gini Index is going to be equal to 2 times the integral from 0 to 1 of x minus f of x. And for 2013, it was x to the 2.6 with respect to x. Whoops, I always get too close to that. So here's our setup. So 2 times the integral from 0 to 1 of x minus x to the 2.6. And believe it or not, that's all we have to type into our calculator. So you'll get GI equals, and then in Desmos, 2 times the integral from 0 to 1 of parentheses x minus x to the 2.6 with respect to x. And we get that the Gini index for 2013 is 0.44 repeating. Okay. And then let's go ahead and do it for 2025. So for B, our Gini index would be 2 times the integral from 0 to 1 of x minus x to the 1.8 dx. And here we'd get again 2 times the integral from 0 to 1 of x minus x to the 1.8. Oops, wrong way. Dx. And we get 0.29. Okay. So based on our results, I guess what could you guys tell me from the results? Because remember, the closer you are to 0, the more income is being equally distributed. And the closer you are to 1, the more income is being unequally distributed. So what do you guys think?
The index went down, so it's closer to 0. So income will be more evenly distributed.
In 2025, right?
Right around the corner.
If we make it. There you go. Okay, cool. There it is. So yeah, so in 2013, the Gini index was 0.44. So that's still not a bad number, but not all income was possibly being equally distributed. And then in 2025, it is predicted that the Gini index will go down to 0.29, which means if the closer you are to 0, the closer you are to having income more equally distributed. All right, and that's it. That's 13.1.